In this video I'm going to illustrate how a feature of the calculator property page on the Spectrum Processing Dialog Window can be used to evaluate a peak model such as the one we see here. And the option that I'm going to use is this Interpolate Spectra. We'll begin though by looking at the peak model. So bringing up the annotation dialog window, I'd like to see easily the constraints that are associated with this peak model, and that is possible if I use the component option on the annotation dialog window and I include constraints. I will leave the line shape there so I can see the line shape. I'll exclude the forward half maximum, the area. I don't even need to know the percentage area or the position. I would just like a table that helps me to understand the structure of this peak model. So line shapes and constraints. And when I press apply, I end up with a table which I would like to just adjust the size so it is easier to see. And the peak model is defined in terms of constraints. I would also argue that line shapes are another form of constraint, but these are only suitable for fitting the data provided we have introduced appropriate constraints between the fitting parameters such as area, forward half maximum and position. So all of these numbers we see here, they are all important in constructing the peak model so that we end up with an answer with a residual that has a residual standard deviation close to unity and a relatively random looking residual plot. However, this is just one example of data, and what I'm going to do is create a set of data that I can then apply this peak model to the data where we have varying proportions of the copper and the platinum. In an ideal world we would have samples and the experimental time to measure a range of samples with different proportions of copper and platinum, and that would give us the test that would allow us to grow confidence in the peak model. However, in the absence of that, then there is a simple tool on the Spectrum Processing Dialog Window, the calculator property page, and it's, as I said, the Interpolate Spectra. In other words, if I can find two spectra that represent one mostly platinum and one mostly copper, using this option I can construct a whole set of spectra with different proportions of copper and platinum. While the calculator allows us to interpolate spectra and generate different proportions of platinum and copper, there's no substitute for data itself. And in this example I'm going to use a different measurement from a different file. So these are measurements that were performed using the same instrument and on different samples, and we have two for which there is predominantly platinum and predominantly copper. So from this I can now construct a set of spectra that are a reasonable test. These are not the data that the peak model was applied to, so I can take these, bring up the Spectrum Processing Dialog Window, calculator property page, set my increment to 2 and then interpolate these two spectra. The reason I've got the increment set to 2 is because the interpolation will create a set of VAMAS blocks starting with a 0 index and ending with 100. So entering an increment of 2 means that I will end up with 51 spectra in different proportions of platinum and copper. So when I press the button I end up with a new file, and the new file contains a set of spectra, all of which evolve from the copper through to the platinum. So what I'd like to do is transfer my peak model to that newly created VAMAS file with the new spectra. So I'm going to propagate regions, components, and I'll autofit, and you can see they are all selected in the different file. This is the interpolated file. They're all called Cu3p, but They actually are a combination of, by the way of construction, and then I just say OK, and the propagation takes the peak model we see here and applies it to all of the data in the newly created file. So here's the one that is mostly platinum. There's a reasonable fit here. It could be better, but it's probably a reasonable measure of how much platinum there is in these data. And then start to move down the list. We are increasing the proportion of copper, and we can see that in fact the copper and the platinum are available for measurement by this peak model. The peak model is particularly interesting because it's including both the photoemission peaks as components and also components that are representative of Shirley backgrounds that are associated with these photoemission peaks. And while at different points in this combination of copper and platinum there's nothing obviously strange about the fit, there is something interesting about the fit we see here, and that is that despite there being no apparent photoemission from the platinum, in order to fit the copper 3p doublet, we have introduced into the background a shape that is associated with the platinum. And that actually makes some sense, because the sample was prepared by depositing copper metal onto a platinum substrate to the thickness that the platinum was not present in the photoemission peaks. But even so, it's possible that inelastically scattered signal from the platinum might contribute to the background shape, and that certainly seems to be an indication from the experiment I've just performed, that when I go up you can see where there's a little bit of platinum, that shape is there, and it is much more pronounced in these small peaks than the peaks themselves. So these represent photoemission signal that is scattered by either platinum or the copper en route to the spectrum that we see here, that is mostly representative of the copper. Attempting to use a peak model that involves asymmetric line shapes and relatively broad structures might be questionable. It certainly is fraught with danger that, depending on the choice of the asymmetry, we may alter the relative proportion of the copper. But why would you choose then to fit the data from platinum and copper if there are other photoemission peaks that you might use to work out the ratio of copper to the platinum? Well, one reason is that these are both at the same kinetic energy, so this eliminates escape depth and transmission, and it also means that the carbon overlayer, any adventitious material, it won't influence the ratio of these two peaks because they're at the same kinetic energy. However, the real reason why we would construct a peak model of this form is found in the survey measurement, where we can see that there genuinely is a lot of adventitious carbon on the surface. This is the carbon peak, this is the carbon Auger peak, and you can see that the Auger peak is declining and it's present, and it's at a very low kinetic energy. So the fact that we've got carbon here and the shape of the background here, well, that suggests that the carbon is at the surface, and it is responsible for the shapes that we see predominantly in the background signal. So here we have the platinum 4f and copper 3p. So we see copper and platinum at this point. However, if we go down the kinetic energy, this overlayer is producing a profound influence on the background and also the peaks. The photoemission peak for copper 3s, for example, that's about unity in terms of a relative sensitivity in terms of scope of cross sections. The copper 2p ought to be about 25 or slightly more than 25 times larger than the copper 3s, and since it has to be that much larger than this peak, and it isn't. If we were going to quantify between the copper 2p and, say, the results from the platinum 4f, we would need to scale results from the copper. So whenever you measure a peak area and then you scale that peak area, which we do anyway with transmission, escape depth and relative sensitivity factors, if we then have to account for an overlay which requires an amplification of the signal in order to compare from low kinetic energy to high kinetic energy, then we are also amplifying the error in our calculation. And this is further emphasized by looking at the copper 2s. This ought to be 5 times the intensity of this copper 3s. And there's barely any information here about the copper 2s. So this would be seriously in error if we attempted to estimate based on the copper 2s and then compare it to the copper 3s. So appreciating the influence of this carbon on the sample and the fact that there really aren't any other platinum peaks that appear in the data, they are all now inversely scattered signal that appears in the background, that we really don't have much options other than the platinum 4f and the copper 3p.